Transistors on a microchip, seen through an electron scan microscope. They process electrical impulses at incredible speed. Switching processes can only be followed when they're filmed in ultra-slow motion. As tiny as they are, today's world of science and technology would be inconceivable without transistors and microchips. Man could never have ventured into space without the help of microelectronics. Microelectronics is the key technology of our age, and its development possibilities have by no means been exhausted. The success story began in December 1947. Today, the transistor is often described as the most important invention of the 20th century. It is the brainchild of 3 researchers at the famous Bell Laboratories in Murray Hill on the east coast of the United States. The creators of the transistor were John Bardeen, a brilliant theoretical physicist who was new to the Bell team, William Shockley, the head of a semiconductor research project at Bell, and Walter Brattain, an experienced experimental physicist with the Bell Company. The transistor acts as a switch or amplifier for electrical impulses. It provided scientists with a fascinating field of research because the secret of the transistor lies in its materials, semiconductors, elements like germanium and silicon. Normally poor conductors of electricity, their conductivity can be specifically improved through chemical change. In 1874, German physicist Carl Ferdinand Braun discovered the rectifying properties of semiconductors and in doing so laid the foundations for microelectronics. Around the turn of the century, Braun utilized the rectifying effect to construct a crystal detector. It remained the only efficient receiver rectifier for telegraphy and radio for many years, in fact until the electron valve was perfected. This first description of a triode, as it's known, stems from Sir John Ambrose Fleming. Like the crystal detector, the electron valve acted as a rectifier and an amplifier. However, it was considerably more efficient and more reliable. The electron valve quickly became the central component of all amplifier systems and radio receivers. The valve permitted the production of powerful radio sets at prices many people could at last afford. It was in the mid-20s that the great era of radio began. People became avid listeners. Scientific progress to the benefit of millions. For years, the electron valve was unrivaled. But when scientists in the field of radar technology began to work with ultra-high frequency signals, the electron valve proved too slow. As a result, the crystal rectifier celebrated a comeback as a receiver for radar waves. In appearance, it had little in common with Carl Ferdinand Braun's original model, but the semiconductor principle remained the same. With the crystal rectifier, in the 1940s, radar technology progressed. As a result, many scientists showed a renewed interest in semiconductors. The time was right for a completely new component, an electronic switch and amplifier based on semiconductors. Consequently, 3 talented physicists came together in a Bell Telephone Company research program: William Shockley, John Bardeen, and Walter Brattain. In 1947, the scientists at Bell had already spent 2 years searching for a semiconductor configuration that would make electronic amplification possible. This meant specifically influencing the conductivity of the semiconducting material. John Bardeen, the theoretician, regarded germanium as suitable if positively charged foreign atoms could be introduced into it. The requisite experiment was devised by Walter Brattain, the practician. He soldered germanium onto a metal disc with 2 gold contacts less than 1/10 of a millimeter away. The intention was for current to flow from one contact, the emitter, through the germanium to a second contact, the collector. Bardeen and Brattain hoped that the flow of current would have an amplifying effect because of the close proximity of the gold contacts to the germanium. In December 1947, they tested a semiconductor configuration of this kind in the laboratory with a telephone circuit. When the point contact transistor, as it was known, was switched on, the sound volume on the telephone increased considerably. The collector showed a 50-fold increase in the amplification of the electrical signal. This scientific sensation earned no more than a brief mention in the New York Times. Bardeen, Brattain and their boss, Shockley, hadn't yet achieved their goal. The charge conditions in the point contact transistor were anything but stable. Sometimes it worked, sometimes it didn't. The solution to the problem was Shockley's junction transistor. It was only in this form that the transistor effect, discovered by Bardeen and Brattain, became a stable and calculable quantity, a prerequisite if the transistor was to be a global success. The principle behind the junction transistor is as follows. In their pure state, materials like germanium or silicon are poor conductors of electricity. But this situation changes when free-moving charge carriers are added through the introduction of foreign atoms. This process is known as doping. When a semiconducting layer doped with negative charge carriers comes into contact with a positively doped layer, current only flows from N to P. That's how a diode works. Basically, a junction transistor consists of 2 diodes connected in opposition. The negatively doped layer acts as an emitter, the other as a collector. The positively doped layer is the base. If a negative voltage of, say, 0.7 volts is applied to the emitter, a flow of electrons takes place through the emitter to the base. If the base layer is very thin, the majority of these electrons will pass into the powerful field between the collector and the base and flow to the collector. If a working resistance is incorporated into the collector circuit, minor signal voltages in the emitter circuit produce major signal voltages at the working resistance. The transistor acts as a voltage amplifier. A diagram for an integrated circuit. Transistors and other components are interconnected on a circuit board. An intermediate stage in the development of the transistor into the microchip, which was accelerated primarily by NASA's Moonflight program. The program required highly efficient computers, but were also extremely light and reliable. The development of the microchip in the 60s finally permitted their construction. Less than 20 years had passed since the appearance of Shockley's first junction transistor. Series production soon revealed one major drawback. The junction transistor had to be laboriously soldered together. The margin for error was too great. The situation only changed with the use of a new manufacturing process and a new semiconductor. Silicon, the main component of sand, and after oxygen, the second most common element on Earth. The researchers grew pure silicon crystals in the form of rods, so that transistors could be manufactured from them in one piece. The silicon is cut into thin slices known as wafers. Now, several transistors could be produced from one wafer simultaneously, initially several dozen, and soon several hundred. With the new planar process, complete transistors could now be manufactured from one and the same piece of silicon. There was no need for soldering anymore. The various layers were created in many successive etching and doping operations. The planar technique made more and more complex configurations possible. As a result, production costs plummeted, and at the same time transistors became increasingly smaller and more efficient. Computer technology in particular benefited from this development. Compared with valve-based devices, transistorized computers were much smaller and they consumed only a fraction as much energy. New products like the legendary transistor radio appeared on the scene, changing the lives of millions of people. The age of electronics was about to dawn. The invention by Bardeen, Brattain and Shockley had conquered the world at lightning speed. Today, we have long since grown used to the blessings of microelectronics. Microchips make many things possible which our grandfathers couldn't have dreamt of. Up to 100 million transistors and components can fit into an area of 1 square centimetre. Manufacturing such ultrafine structures calls for absolutely sterile conditions. The slightest impurities could ruin an entire production batch. The production process is highly complex. First of all, the circuit diagram for the microchip is transferred to glass masks by means of electron beams. Pure silicon is still the material used in the manufacture of most microchips. Modern chip production is still based on the planar process. After being coated with photoresist, a thin photosensitive film, the silicon wafer is exposed through the glass masks. In this way, circuit diagrams for many microchips are applied to the wafer at the same time. This occurs in several layers, one above the other. After the developing etching stages, bombardment with foreign atoms takes place in order to specifically change the electrical properties of the silicon. In all, some 500 individual operations are necessary to produce a complete chip on the wafer. Microchips, tiny in size, gigantic in their capability. A 64 megabit chip can store and then read out the content of 4,000 typewritten pages in a fraction of a second. The next 3 generations of microchips will probably follow the trend that has prevailed up to now in the field of microelectronics. With each stage of development, new components have been roughly 4 times more efficient than their predecessors, at regular intervals of around 3 years. This has been the case ever since the first transistor was invented in the Bell laboratories back in December 1947. By William Shockley, John Bardeen and Walter Brattain, who in 1956 were awarded the Nobel Prize for Physics for their services to semiconductor technology.